Have you ever noticed how some apps just fly? You tap a button and boom, the results are there, instantly. And then there are others that feel like they're wading through molasses, leaving you staring at that frustrating spinning wheel. It's a common experience, right? But what's actually happening behind the scenes that makes one so smooth and the other so sluggish? Today, we're pulling back the curtain on that digital mystery. Our mission is to understand the fundamental concepts that dictate how fast and efficiently our software runs. We're talking about things like Big O notation, the crucial data structures that organize information, and the foundational algorithms that process it. And this isn't just for software developers, really. Understanding these principles gives you a powerful lens to view the digital world, and frankly, it's pretty fascinating stuff.
It truly is, yeah. This deep dive isn't about memorizing code snippets or anything. It's about grasping the underlying principles of efficiency. These things underpin almost every digital interaction you have daily. We'll explore how core decisions about how data is organized and manipulated can dramatically impact performance, making the difference between, an instant response and a really frustrating wait.
Okay, so let's jump right into what feels like the secret language of efficiency.
Mm-hmm.
Big O notation.
Yeah.
It sounds intimidating. What exactly is Big O notation? Is it about exact speed tests, like saying this program finishes in precisely 2.3 seconds?
No, not at all. That's a common misconception. Big O isn't about precise execution time. Instead, it's a way to describe an algorithm's performance or complexity. Specifically, it focuses on how its runtime or memory usage scales as the size of the input data grows.
Scale.
Yeah, we're looking at the rate of growth, not a stopwatch measurement. So when we talk about how runtime scales, we call that time complexity. How does the time needed change as you give it more data? And when we talk about how memory usage scales with the input size, that's space complexity. How much more memory does it need? It's always about how things behave as in the size of your input gets larger and larger.
Ah, okay. I think I'm starting to get the distinction there. So it's about predicting performance for really big problems, not just tiny ones. Could you walk us through some of the most common ways this rate of growth actually shows up?
Absolutely. Let's start with the most efficient scenarios. These are the ones developers often strive for. First, we have O1, or constant time.
O1, constant.
Right. This means the algorithm takes roughly the same amount of time, no matter how large the input data gets.
Okay, so like if I'm looking for a specific house on a street and I have its exact address, it takes me the same amount of time to find it, whether the street has 10 houses or 10,000.
Exactly. Or, in software terms, accessing an element in an array by its index. Say, array 5. The computer knows exactly where to go. Direct access.
Got it. Makes sense. What's next?
Then there's a log n, or logarithmic time. This is incredibly efficient.
Logarithmic.
Because the amount of work required effectively halves, or reduces significantly, with each step. It grows much slower than the input size.
Right. A perfect example is binary search in a sorted array, isn't it?
Precisely.
Imagine looking for a specific word in a massive dictionary. You don't start at A and flip every page. You open to the middle. Is your word before or after? Then you open to the middle of that half and so on. You discard huge chunks.
That halving of the search space is the key. It's why it's so powerful for large data sets. Next up, we have ON, or linear time.
Okay, linear, like a straight line graph.
Pretty much. Here, the runtime grows directly in proportion to the input size. If your input doubles, the runtime roughly doubles.
This feels intuitive, like scanning every item on a grocery list. If you have 10 items, it takes X amount of time. 20 items, roughly 2X time. You have to look at each one.
Exactly. A very common pattern. Then there's ON, log n, or log linear time. This one pops up a lot.
And I'll log in.
Yeah, it's very common for efficient sorting algorithms. Think merge sort or quick sort on average. Better than ON2, but not quite as fast as ON.
Okay, which brings us to the less efficient ones.
Right, like ON2 or quadratic time.
Yeah.
Here, the runtime grows by the square of the input size, double the input, and the time roughly quadruples.
Oof, yeah, this often involves nested loops, right?
Yeah.
Where for every item, you're doing something with every other item, like trying to find every single unique pair of people in a crowd. If you have 10 people, maybe 100 comparisons. But 100 people, suddenly it's 10,000 comparisons.
Yeah.
It blows up fast.
It really does. And what's truly astonishing here is how quickly the differences escalate between these categories. Choosing an ON, or O-log-N approach over an ON2 approach, well, it can literally mean the difference between an instant result and a program that takes minutes, hours, even years to complete for very large inputs.
Wow.
Years!
Absolutely. Think about a major social media app. If their feed loading algorithm was ON2 for millions of users, Well, you wouldn't use the app. It would be unusable. That n-squared factor is brutal at scale.
Okay, that really puts it in perspective, a huge difference. So with Big O, we have the language to describe efficiency. But efficiency for what? It's like knowing how fast you can chop vegetables is one thing, but it also depends on how those vegetables are organized in your kitchen, right?
And that's a great analogy.
That's where our ingredients, or rather our data structures, come in.
Precisely. Choosing the right data structure is absolutely crucial. It directly dictates how quickly you can find, add, or remove information. And that, in turn, heavily impacts the overall algorithm performance. So where do we start? What are the fundamental building blocks?
Let's start with the most basic, probably, arrays and strings. They're fundamental collections. The key insight with arrays is that elements are stored in a contiguous block of memory, one right after the other.
Contiguous, meaning all together.
Exactly. This allows for super efficient, O1, constant time access to any element if you know its index. The computer can just calculate its exact memory address and jump right to it.
Ah, like our book page number example again. Instant access if you know the page. But what about when arrays need to grow? I know some programming languages have dynamic arrays like array lists or vectors that can resize. Does that mess with the O1?
That's a good question. Dynamic arrays do resize. When they run out of space, they typically allocate a new, larger block of memory, often double the size, copy all the old elements over, and then add the new one. That specific resizing operation is slower, maybe ON because you copy everything. But it happens infrequently enough that the average cost of adding an element, called the amortized cost, is still considered O1. It feels fast most of the time.
Amortized O1.
Okay, got it. So usually fast, occasionally slower when it resizes. And with arrays, there are some really clever patterns people use, right? You mentioned two pointers.
Yes, a very common technique. You use two indices or pointers that move through the array, often towards each other or in the same direction, to solve problems efficiently.
Like checking if a word is a palindrome. Start pointers at the beginning and end, move inwards, checking if letters match.
Exactly. Or the sliding window technique.
Sliding window.
Yeah, you maintain a window of elements, a subarray, and slide it across the main array to find something, like the maximum sum of a subarray of fixed size. Very useful for sequence problems.
Cool patterns. Okay, what's next after arrays?
How about structures defined by access rules, like stacks and queues? These are abstract data types,
Abstract.
meaning they're defined by how you interact with them, not necessarily how they're built underneath, though often arrays or linked lists are used. A stack follows LIFO, last in, first out.
LIFO, like a stack of plates. The last one you put on top is the first one you take off. Perfect analogy. Or the undo button in software. The last action you did, last in, is the first one undone, first out. Its core operations are push, add to top, pop, remove from top, and peek. Just look at the top element without removing it. All typically O1.
In the queue.
A queue is the opposite. FIFO, first in, first out.
Like a line at the grocery store, right?
Yeah.
First person in line is the first person served.
Exactly. Think printer queues, customer service lines. The first item added is the first one removed. Operations are usually called on queue, add to the back, and to queue, remove from the front. Also typically O1.
Okay, stacks and queues. Clear rules. Now, what about linked lists? You mentioned they can be used to build stacks and queues. How are they different from arrays?
Big difference. Unlike arrays, linked list elements called nodes are not stored contiguously in memory. Instead, each node contains its data and a pointer, like a little arrow, that points to the memory location of the next node in the sequence.
Ah, so it's like a chain or a treasure hunt, where each clue tells you where the next clue is hidden.
Exactly. That's a great way to picture it. This structure gives them flexibility. Adding or removing an element in the middle is often easier than with an array because you just need to change the pointers, not shift all subsequent elements.
But searching takes longer, right? You can't just jump to an index.
Correct. Finding an element usually requires traversing the list from the beginning, which is ON, trade-offs again. And there are different types. Singly linked, pointers go one way. Doubly linked, pointers go both forwards and backwards. And circular, the last node points back to the first.
Okay. And you mentioned a classic problem with linked lists, cycle detection. How do you find out if a treasure hunt accidentally leads you back to a clue you've already found?
Right, if the list loops back on itself. The most famous solution is brilliant, Floyd's tortoise and hare algorithm.
Tortoise and hare.
Yeah, you use two pointers. One moves one step at a time, the tortoise. The other moves two steps at a time, the hare. If there's a cycle, the faster hare will eventually lap the slower tortoise, and they'll meet inside the loop.
Wow, that's clever. Okay, so linked lists offer flexibility, but maybe aren't the fastest for lookups. What if you need that instant lookup, like finding a contact's phone number in a massive digital address book without scanning the whole thing?
Now you're talking about arguably one of the most useful data structures for optimizing algorithms. The hash table, often called a hash map or dictionary,
Hash table. Okay, I hear this one mentioned a lot. Why is it so special?
because it provides incredibly fast average time complexity for lookups, insertions, and deletions. We're talking O1 on average.
Oh, one average. That's constant time, like the array index lookup. How does it manage that without knowing the index beforehand?
It's quite ingenious. It uses a special function called a hashing function. You feed the key, like a person's name, into this function, and it computes an index number. This index tells the hash table where to store or find the associated value, like the phone number, in an underlying array, often called buckets.
So it calculates the storage spot directly from the key.
Exactly. In the ideal case, you just compute the hash, go to that index, and bam, there's your data. Or you know that's where it should be if it exists.
That sounds amazing. Why? On average, though, what's the catch?
The catch is collisions. What happens if the hashing function computes the same index for two different keys? That's a collision.
Ah, right. Multiple keys trying to fit in the same bucket.
Exactly. When this happens, the hash table needs a strategy to handle it. Two common ones are chaining, where each bucket can hold a linked list of all the items that hash to that spot.
So you might have a short list to check within the bucket.
Right. Or open addressing, where if a bucket is full, the algorithm probes nearby buckets according to some pattern until it finds an empty slot. Because of collisions, the worst-case scenario for hash table operations can degrade to ON if, say, everything hashes to the same spot and you end up with one giant linked list.
But that's rare with a good hash function.
Very rare with a well-designed hash function and table resizing. So in practice, you almost always get that fantastic O1 average performance. That's why they're everywhere: caches, database indexes, symbol tables, and compilers.
Okay, hash tables are powerful. What about hierarchical data? Things with parent-child relationships.
Now I'm moving to trees. Think of a family tree or an organization chart. A root node at the top branching downwards.
The most common type I hear about is a binary tree.
Right. Each node in a binary tree has at most two children, a left child and a right child. And a special, very useful type is the binary search tree, or BST.
What makes it a search tree?
Its ordering property. For any node in a BST, all values in its left subtree must be less than the node's value, and all values in its right subtree must be greater than the node's value.
Ah, so it's organized. Does that make searching faster?
Definitely. If you're looking for a value, you start at the root. Is your target value smaller? Go left. Is it larger? Go right. You eliminate half the remaining tree at each step, similar to binary search.
So searching is typically O log n.
O log n, on average, for a reasonably balanced BST. If the tree becomes very unbalanced, like a long spindly chain, the worst case can degrade to ON.
Okay. And how do you visit all the nodes in a tree? I think I've heard terms like in-order, pre-order.
Those are tree traversals, different ways to systematically visit every node. In order, left, root, right, is special for BSTs because it visits the nodes in ascending sorted order. Super useful. Pre-order, root, left, right, is often used for copying trees. Post-order, left, right, root, can be used for deleting nodes safely. And there's level order, where you visit nodes level by level, from top to bottom, left to right. It actually uses a queue internally to keep track of nodes at the next level.
Interesting how data structures build on each other. Queue for level order traversal.
Indeed. Now, another fascinating tree structure, highly specialized, is the trie, sometimes called a prefix tree.
Trie, T-R-I-E.
Correct. It's specifically designed for storing and retrieving strings, like words in a dictionary. Each node represents a character. A path from the root down to a node spells out a prefix. If a node is marked as terminal, that path represents a complete word.
That sounds perfect for autocomplete, like when your search bar suggests queries as you type.
Exactly. That's a prime use case. Spell checkers also use tries heavily. The beauty is, searching for a word or prefix of length k is typically okay. The time depends only on the length of the word you're looking for, not the total number of words stored. That's incredibly fast for string operations compared to, say, a BST.
Very cool. Okay, one more tree-related structure. Heaps.
Yes, heaps. They are tree-based, but with a different property. They satisfy the heap property. In a max heap, the value in any parent node is always greater than or equal to the values in its children. So the largest element is always at the root. In a min heap, the parent is always less than or equal to its children, so the smallest element is always at the root.
Okay, so easy access to the biggest or smallest item. What's the main application for that?
They are perfect for implementing a priority queue.
Priority queue. Like a queue, but some items get to cut in line.
Essentially, yes. It's an abstract data type where each element has an associated priority. When you dequeue, you always get the element with the highest or lowest, depending on min-max heap priority.
How efficient are heaps?
Finding the min or max element at the root is O1, constant time, just peak. Inserting a new element or removing the min-max element involves maintaining the heap property, which takes O log n time, still very efficient.
And where might you see priority queues or heaps in action?
Lots of places. Operating system task schedulers often use them to run the highest priority process first. Algorithms for finding the shortest path in graphs, like Dijkstra's, often use a min-heap, or finding the top K items in a huge stream of data, like the top 10 most viewed products on an e-commerce site in real time. You can maintain a min-heap of size K.
Wow, okay. That's a lot of powerful building blocks. Arrays, stacks, queues, linked lists, hash tables, trees, tries, heaps. So we've covered the language of efficiency, big O, and these fundamental data structures. Now, how do we actually do things with this organized data? Let's talk about some fundamental algorithms.
Right. Algorithms are the recipes, the step-by-step procedures for solving problems using these data structures, and a classic fundamental problem is sorting.
Arranging things in order. Seems simple, but I guess there are many ways to do it.
Many ways, each with different characteristics. Let's touch on a few key ones. First, quicksort. It's a very popular divide and conquer algorithm.
Divide and conquer.
Yeah, it works by picking an element called the pivot. Then it rearranges the array so all elements smaller than the pivot are to its left and all elements larger are to its right. It's called partitioning. Then it recursively applies the same process to the left and right subarrays.
Okay, how fast is it?
Its average time complexity is excellent, O(n) log n. It's often very fast in practice because its inner loop is simple. However, its worst-case performance can be O(n)(2). This might happen if you consistently pick bad pivots, like the smallest or largest element in an already sorted or reverse-sorted array.
So it's usually fast, but has a potential Achilles heel. Any other key features?
It's typically an in-place sort, meaning it sorts the array using only a small constant amount of extra memory for recursion stack space usually. But crucially, it's not a stable sort.
Not stable. Remind me what that means again.
Stable means if you have two elements with the same value, or same sorting key, their original relative order is preserved after sorting. Quicksort doesn't guarantee this. If you sort people first by city, then by name using quicksort, two people from the same city might have their original name order swapped.
Got it. Important that the original order matters for ties.
Yep.
Okay, who's next?
Mergesort, another divide and conquer algorithm. It works differently. It repeatedly divides the array into two halves until you have arrays of size 1, which are inherently sorted. Then it merges these sorted subarrays back together, creating larger sorted arrays until the whole array is sorted.
How does it compare to quicksort?
Its main advantage is its consistency. Mergesort's time complexity is O(n) log n in all cases, best, average, and worst. No O(n)(2) surprises. And importantly, Mergesort is a stable sort. It preserves that original relative order for equal elements.
Sounds great. Is there a downside?
Yes, its main downside is space. That merging step typically requires O(n) auxiliary space. It needs extra memory roughly proportional to the size of the input array to hold the merge results temporarily.
The time versus space trade-off again. Okay, one more. Heap sort.
Right, heap sort. This one cleverly uses the heap data structure we just discussed. First, it builds a max heap from the input array. This puts the largest element at the root, the first position. Then it swaps this largest element with the last element in the array, effectively putting the largest element in its final sorted position. It then reduces the heap size by 1, heapifies the root to restore the max heap property, and repeats swap root with last element of current heap, produce size, heapify.
Clever. And its performance.
Like Mergesort, it's O(n) log n, time complexity in all cases. And like Quicksort, it's an in-place sort requiring only O(1) extra space.
Best of both worlds. O(n) log n, time O(1) space.
Almost. The catch.
Okay.
Like Quicksort, heap sort is not a stable sort.
Always a trade-off. So many choices for sorting. It really highlights that there's no single best way, huh?
Exactly. It depends entirely on the constraints. Do you need guaranteed O(n) log n? Is memory extremely limited? Does stability matter? These questions guide the choice.
Fascinating. Okay, besides sorting, what's another really fundamental algorithm? You mentioned binary search earlier.
Yes, binary search is incredibly important, not just for searching itself, but as a pattern.
And the key thing is,
The array must be sorted first. That's non-negotiable for standard binary search.
right, and how does it work again?
You maintain a search interval within the sorted array. You look at the middle element of the current interval. If it's your target, you're done. If your target is smaller, you know it must be in the left half, so you discard the right half. If your target is larger, you discard the left half. You repeat this process, having the search space with each comparison.
Which gives it that amazing.
Time complexity. Logarithmic. Super fast for searching large, sorted datasets.
It feels like a fundamental building block for solving more complex problems, too, not just finding a number.
Absolutely. The idea of repeatedly narrowing down possibilities based on comparisons in a sorted or structured space is a core algorithmic technique.
Wow. Okay, so we've taken quite a journey here. We've looked at Big O notation, the language for talking about performance and how things scale. We explored those essential building blocks, arrays, linked lists, hash tables, trees in their various forms like BSTs, tries, and heaps, the containers for our data. And we touched on some crucial algorithms that put that data to work, like different sorting methods and the super efficient binary search.
Yeah, and it's crucial to remember these aren't just abstract computer science theories locked away in textbooks. They are the invisible architecture, the engines driving almost every digital interaction you have, the speed of your Google search results. That relies heavily on optimized data structures and search algorithms, how quickly your favorite app loads its content. Same thing. Understanding these core ideas give you a really powerful lens to view the digital world and appreciate the, frankly, incredible engineering that makes it all work smoothly most of the time.
Absolutely. So the next time you experience that lightning fast search, or maybe a frustratingly slow application, you'll have a much deeper understanding of the clever choices, or perhaps the compromises and trade-offs that were made behind the scenes. It's all about managing complexity and resources.
And maybe think about it this way. How might understanding these concepts of efficiency, organization, and trade-offs help you? Maybe not in writing code, but in optimizing a process in your own life or work. Think about the data you handle, everyday emails, tasks, information. What are the algorithms, the steps you use to manage it? Could they be more efficient?
That's a great thought to leave folks with. It's about structured thinking, really.
Mm,
Well, that's it for this deep dive. Thank you so much for joining us on this journey into the fundamentals of digital efficiency.
my pleasure.